Alright, this is a classic problem that comes up all the time in interviews, merging overlapping intervals. Imagine you've got a bunch of meeting times on a calendar, and some of them overlap. You want to combine those overlapping ones into single blocks. Here's the key insight: if we sort everything by start time first, then overlapping intervals will always be sitting right next to each other. That one sorting step turns a messy problem into a simple linear scan. First things first, we sort the intervals by their start value. This is the foundation of the entire algorithm. Think of it like lining up index cards from earliest to latest. Once they're in order, we only ever need to look at the last interval we've processed to decide if something overlaps. Without this sort, we'd be comparing everything to everything, total nightmare. Now we set up our result list called merged, and we seed it with the very first interval. Why? Because we need a starting point to compare against. Think of it as putting the first puzzle piece on the table, everything else will build off of this. Since we sorted already, this first interval has the smallest start time. Here's where the magic happens: we loop through every remaining interval starting from index 1. Notice the nice Python unpacking here: we grab start and end directly from each interval. Super clean, super readable. For each one, we're gonna ask one simple question: does this overlap with what we've already got? This is the critical check. If the current interval's start is less than or equal to the end of the last merged interval, we have overlap. Think about it on a number line: if my new interval starts before the previous one ends, they're touching or crossing. Because we sorted by start time, this single comparison is all we need. Beautiful, right? When we detect overlap, we merge by extending the end of the last interval in our result. We take the max of both ends because, and this is the key insight, the new interval might be completely contained within the existing one. Imagine interval 1 to 10 and then 3 to 5 shows up. We don't want to shrink our range, so max keeps us safe. If there's no overlap, the current interval stands on its own, it's a brand new group. So we just append it to our merged list as is. This becomes the new last interval that future intervals will compare against. It's like starting a fresh cluster when there's a gap on the timeline. And finally, we return our merged list containing all the non-overlapping intervals. Every original interval is accounted for: either it got absorbed into an existing one or it started a new entry. Clean and simple, one pass through the data after sorting. Time complexity is O of n log n because of the sort. The merge pass itself is just O of n. Space complexity is O of n for the output list. Here's your takeaway: whenever you see interval problems, your first instinct should be sort. Sorting transforms chaos into order, and suddenly overlaps become neighbors you can handle one at a time. Remember that, and you'll crush these problems every single time.